Hello everyone, my name is Cameron and I'm from the Math Center. So for those of you that don't know, the University Math Center is a free service that is paid for by your tuition. And basically what we are is we're a free drop-in tutoring center for math, statistics, and physics. So I know this is a Math 181 course, I believe. Is that correct?
Yeah,
Number
that's
one.
correct.
And but some of you may be taking a physics course later on or maybe a statistics course. So for your future courses as well, the Math Center is always open. And so, like I said, we're a free drop-in tutoring center. So what that means is all you need to do is you can either show up to our in-person place, which is the third floor of the Pennington Student Achievement Center. So if you walk into kind of the food area of the Pennington Student Achievement Center building, go up the stairs, first door on the right is the Math Center. And so all you need to enter the Math Center is just your Wolf card. And we just need that so that we can keep track of who enters and who leaves. You can also join via Zoom. And so if you go to our website, which I think if I can share screen, I can just really quickly, I should be able to, yeah, that should work. So can you guys see my screen? So if you Google UNR Math Center, should be the first link that pops up. And if you'll notice, there's this nice link here that says access the Math Center via Zoom. So if you click on that, you can join our online Zoom meeting, which is always open during our hours. And you can also get tutored that way. Again, you need your Wolf card and we'll just have you enter like the bar number and you'll message the host so that we can keep track that you're there. But that's a really nice option in case you're not comfortable coming into the Math Center in person, or if you're not in Reno, particularly for the semester. And so our hours are from, I believe they're written here, Monday through Thursday, 9 a.m. to 7 p.m. and Fridays from 9 a.m. to 4 p.m. And so we also have a few nice things on our website that are like review sessions. So we have a review session schedule. So this is our Google Calendar. And so it's probably empty right now, but for every class, we do review sessions before your exams. So it's a 90-minute session where we just go over the topics for your exam to help prepare you for them. And if you go on the website, you can see eventually this will get updated. It's a little early in the semester, but we'll post here what the classes are and you can see what tutor is leading them and at what time it will be. You'll also probably get an email. And then the last couple things on here, we do calculator rentals. So if you need a graphing calculator for any course, you can stop by the Math Center and we can rent out a calculator to you. I believe it's $20 per semester. And when you come in here, we'll show you how to deal with the payment for that and everything. So if you are interested in that, you can stop by. We also, if you want to come in person, we have, I think this is 20 now since we have every other computer in use, but we have computer lab stations with the mathematics and statistics software. So WebAssign, which is what is used for this course, and then also some other softwares that are used for other courses you may be in. And so I think that's listed here. And then I guess the last thing is our tutoring schedule. So if you like a particular tutor and you want to see when they work, our schedule is listed when everyone works throughout the week. Blue means they're online. Black means they work in person. And then I believe the last thing is we have this nice heat map. And so it's probably in here. So if you go to the bottom of this page, you can click on a particular course. So this says when tutors are working, but if you click on, say, math, what are we in, 181? Oh, that's probably, 181 is probably not listed because every tutor who works here should be able to tutor Calc 1. But for example, for other courses, there's a nice heat map and it shows how many tutors are on the floor that can help with that at a given point in time. So if you are in another course and you want to see if there's a tutor who can help, you can reference this and it'll show us or show you how many tutors we have on at a particular time. Okay, I think that covers most things. Are there any questions before I go? Okay, well, like I said, it's a free drop-in tutoring center. So if you need help, I highly encourage you to stop by at some point. We're all here to help you and help you to succeed in this course. So thank you. And Professor
Oh,
Ohemeng.
okay. You're welcome, Cameron. Thanks for sharing that information with us. Okay, so let's get on to work. Before we begin, please, do you have any comments before we start? Do you have any issues, any questions? Okay, so I think on my roster on my Nevada, I have more people than I have on WebAssign, right? And homework in WebAssign is going to be due, I think, on Tuesday, which is tomorrow. So please, if you're not yet on WebAssign, please make it a point to try and get on, right, as soon as you can. So that'll be something to know. And if you join the class late too, please do let me know so that I send you some useful information, right, to get you set up for the class. Okay, so with that said, with that out of the way, let's get on to work. So the last time we were looking at section 2.2, right? Let me just share. Okay, let me share my desktop. Oh no, PowerPoint. Come on. Function F5. Something in the chat. I'm unable to buy subscription. So what should I? Oh yeah, so Thomas, regarding your question about WebAssign subscription, right? On the syllabus, you recall that I gave you some information on what to do when you encounter any difficulties. They have their number there, like the WebAssign customer service, customer support or something. Yeah, so you can contact them, right? If you can't see it, let me know. I'll check it out and send it to you again. Yeah. Okay, you're welcome. So shift second 5. Okay, please, I'm sharing the PowerPoint slide. If you can't see, do let me know. Okay, so last week, right, we started looking at how to get limits, right? How to obtain limits. And we said we're focusing on two kinds of obtaining the limits. So either using the graphical technique or using the numerical. And then we said for the graphical technique, you mostly be using this for the entire class, right? But numerical, you won't be doing something like that, right? So we started looking at how to use the numerical, and then I pointed out some pitfalls which you encounter when you're using the numerical technique, right? So one pitfall we saw was this one, a case whereby when you take closer and closer values, it's as if the limit is 0, but that is not true because it's just approximation difficulties with the calculator that's creating that error, right? So this could lie. Your guess will be wrong, right? The correct answer is 1/6, and that one you don't need to take it too close, and you still get your answer, right? So we saw this. This was the last example we saw, right? And I showed you this link that you can go to check for these kind of cases. Now, let's look at another example, right? As I said, at this point, you are just explaining. I won't ask you to use a numerical technique. I won't ask you to use a numerical. So I'm just explaining some pitfalls and stuff, right? So for here, everything has been provided. We don't have to do any calculation, any such numerical computations for now. So for this one, we are asked to find the limit as x approaches 0 of x cubed plus cosine of 5x over 10,000, right? And then for this one, using the numerical technique, we take x value. Since we are looking at x from what? 0 and getting close from this side, from the two sides. You take values like from the right, right? This one is 1, 0.5, 0.1, 0.05, 0.01, right? So that's from the right, taking it closer and closer. And then you are kind of like getting these values. Now, looking at the pattern, you might guess and say, looking at this pattern, it appears this is approaching 0, right? You could probably guess that it's 0, right, from the pattern. But as you take much more closer values of the x, as you take closer and closer, like 0.05, 0.005, and then 0.001, you see that at this 0.0001, it becomes stable, right? Here is 0.001, 0009. And here is 0.001, 0.0000. So you can see from much more closer values of the x that this is in fact not approaching 0, but rather it's approaching what? 0.00001. So that means if you're not careful in some cases and you don't take much more closer numbers, you might guess wrong, right? So this is also showing us another case where it fails, like the guessing is not a perfect thing, or the numerical technique has some issues, right? So our final answer is what? 0.0001 instead of that initial guess of 0. Please, are you okay with this? Okay. So these are just cases where you have to be cautious with the numerical thing, right? With the numerical technique. Now let's talk about one-sided limits. Now, when you look at what we did in 2.1, when we started the whole limit process, we said that we were taking the limit from the right and then from the left. And then we made sure that these two agree on a single answer, that they are both approaching a number. Then we said that that limit is equal to that number, right? It turns out that we can just focus on one part of the limit. Either we are taking only from the right or from the left, right? So that's what one-sided limits are. So one-sided limits are just when you're looking at the limit, instead of looking at it, focusing from two sides, you just be focusing on one side, either from the right or from the left, right? So that's a one-sided limit. So for this one, to illustrate this, we have a function here, which is a piecewise function, right? A function in pieces. So this function h of t is called a Heaviside function. It's called a Heaviside function. It's named after Heaviside, one of the mathematicians or I think physicists. Yeah. So for the Heaviside function, it's 0 if the t is less than 0, and it's 1 if the t is greater than or equal to 0, right? So for this one, if you are asked to find the limit as t approaches 0, right, from the left, right, then what this thing is asking you is, instead of finding the general limit, right, for the general one, we don't have any symbol like this there. You see, I have a superscript minus here. Now, this superscript minus there implies that when I'm taking the limit, instead of looking at the two sides, since the superscript is a negative, I have to focus on only smaller values than 0, right? Only smaller values. It shouldn't be bigger numbers. So only from the left, right? From smaller values. So I'll try numbers like 0.000, and no, this to the level 0. So negative 0.01, something like negative 0.00001, and so on and so forth, right? So that's what I have to focus on. So that's a left-sided limit or left-hand limit. Now, we could also do it for only the right hand, right? So that one, we write it as follows. So the notation is you do t approaches 0, but since you're taking bigger values, you do a superscript plus up here, and then you have the function here. And then for this one, you'll be focusing on what? Only bigger numbers than 0. So if you have 0 here, then you'll be looking at what? Numbers to the side. So something like 0.01, right? 0.0001, and taking it closer and closer. But always, these numbers have to be a little bit bigger than 0, right? So that's a right-hand limit, right? Or approaching this 0 from the right, right? So these are one-sided, right? One-sided limits. So these are the one-sided limits. Now that we have an explanation of what these are, let's try and get the answers to these. Let's get a solution. Now for the Heaviside function, it's a piecewise function, right? So if you are taking the limit as t approaches 0 from the left of h of t, then what would this be? Well, to get this, let me get a graph. The Heaviside function will be like this. Right here, let me graph it here. So this Heaviside function at 0, that's where the partition happens, right? And it's 0 if the t is strictly less than 0. So the Heaviside function is, let me see if I can use several different colors, right? So let me zoom out. Yeah. Okay, so I think I can use several colors here. So this Heaviside function is going to be what? 0 if it's less than 0, right? And then at 0, there's a punch hole at 0. And then it's going to be what? 1. So it's like so. And then it's going to be 1 if it's equal to 0. So 1 is somewhere here. Let's say 1 is here. So it's going to be 1, so shaded point. And then it continues like so. So there's the h of t. That's the Heaviside function, right? So the Heaviside function is 1 for when it's 0 or positive, and then it's 0 when it's negative, right? So this is it. Now, using the graphical technique, you can see that if you're interested in the one-sided limit from the left, then you track the function from here, from this side, from this direction. Now, if you track this, as you approach from the left of 0, what is this approaching? Can anyone help us? I think this is already here. So I was going to ask you guys to contribute. Yeah, so what was this approaching? From the left, it's just going to be 0, right? Using the graphical technique, from the left is going to be 0. So this is equal to 0, right? Now, what about from the right? So from the right to using the graphical technique, you can approach it from this side, from this side, from this side, from this side. And you can see that from the right, as you get closer to the 0, it's approaching what? 1. So that's why we say from the right, this limit is 1. Please, are you okay with that? So that's how you find one-sided limits. Please, any questions on this? Okay. Anybody needs time here? Okay, so that's one-sided. So the notation T with the right arrow and then 0 to the superscript minus indicates that we consider only values of T that are less than 0. And then when you have 0 and then the superscript is plus, then that means you're only considering values of T that are greater than 0, right? So that's the one-sided limit. So let's make a formal definition of one-sided limits. So we write the limit as s approaches a and then superscript minus here, right? Of a function of x equal to L. Then that means this is what we say, this the left-hand limit of f of s as s approaches a, right, is equal to L. If we can make values of f of s arbitrarily close to L by taking x to be sufficiently close to a, with x less than a, right? So that's the notation. Please, are you okay? From the left, that means you have to look at only smaller numbers than a, right? We also have from the right, right? So similarly, we require that s to be greater than a, we get the right-hand limit of f of s as s approaches a is equal to L. And then we write it as this, if you are considering only s values greater than a, right? So this shows us the graphical technique with the one-sided limits. So for this one, if we are looking at this one-sided limit, right, we are asked to find the limit as s approaches a. It's too small. Let me make it big. Shift F5, right? But that one will limit my options on the color I can use. Okay, I'll just use this here. At least it's the bigger option is better here. So let's look at this one. If you have a graph like so, and the question is asking for the one-sided limit as s approaches a from the left. So what do? You first locate the a, and then you track the graph, right? So the graph. Now, since it's from the left, you have to track the graph from the left, not from any other place. And you do it one-sided, so only from the left. So you track the curve. The curve is going, rising. Oh, from the left. Before we cross over the a, we have to be able to identify what this limit is, right? So that will give us this point here, right? And we know that the height here is L, so that means here is L. So using the left-hand limit, or finding the left-hand limit, you're going to get what? L, right? That's why the limit as s approaches a from the left of f of s is L. Now for the right-hand limit too, that one, you track it from the right of the a, right? So looking at the curve, oh, it's rising and falling, and then here, oh, it's approaching this point here. Never cross the point, right? So it's here. So that's also L. So the right-hand limit is also L. So that's how you do it using the graphical technique. Please, any questions on this? Anybody needs time here? Okay. Now, we established a very important rule. Now, the limit, the general limit, right? The limit as s approaches a of f of s is going to be L if and only if the right-hand limit and the left-hand limit are both L, right? So the general limit, right? If you don't specify whether we are moving from the right or the left, you recall that we do it from the two sides, right? This notation here implies you have to do it from the two sides. If you don't see any superscript here, right? That means you're doing it from the two sides. Now it will be equal to L if and only if from the left and from the right are both L. So this is very important, right? It will come up often, right? So that's a theorem here. Now, if and only if in math implies two ways, right? That means that if the general limit as we approach a of f of s is L, then it implies that the one-sided limits are both L. On the other hand, if the one-sided limits are equal to L, then it implies that the limit as you approach the general a is also L, right? So that's the if and only if condition. It implies both ways. If this is true, then that is true. Or if that is true, then this is true. The other one is true, right? Yeah. Please, any questions on this? Okay. Anybody needs time here? Okay, so now this will be an example which I'll ask you guys to help me out, right? At least we've learned how the graphical technique works. So this would be a good way to show, like to see if you really grasp this technique, right? So for here, we are going to use the graphical technique, right? So it says the graph of a function gain is shown in figure 10 and use it to state the values, if they exist, of the following. So please help me out here. Now in this class, what you're going to do is, as I said, if you propose an answer, I'll put it in here. And if we confirm it, then you put like a rectangle around it, right? So for this one, what do you say? Can anyone help us with A? What will be this limit? So you're looking at, this is the G of S function, right? The blue. You're looking at the limit as S approaches to from the left, right? The limit of G of S as S approaches to from the left. What would that be? Does anyone have, what do you say? Please try and let's see if you understand this. Feel free to speak your mind. 3. So I have 3. I have a seconder. So what I'll do is, what you do is, if someone says it, then we will try and see if we can wait for a seconder, right? And then if you get a seconder, then we move on, right? So I have 2 people agreeing on 3. So let's discuss this and see if this is indeed 3. So I'm approaching 2 from the left. Okay, so what do I do? First, locate 2. I have 2 here. Okay. So 2 from the left, that means where should I track the graph? Oh, I should track it from the left. So from this side, it's one-sided. It's a one-sided limit. So going up. Oh, I see from here, right? So that's the point. So that one is what? It's 3. So that's correct. So this is going to be 3. Please, are you okay with that? Yeah. Okay. Can anyone please help us with B? What do you say? B. What do you think? We are looking at the limit of G of S as S approaches 2 from the right. So what would that be? Anyone? Anybody? What do you say? I said, feel free to make your mistakes. We all learn from our mistakes. You can also feel free to unmute yourself and speak. That's also fine. Or use the chat, whatever works. Anybody from the right of 2, what do we get?
Is it 1?
Yeah, so I have 1. Thank you. Feel free to speak your mind. Why? Yeah, 1. Do you have a seconder to 1? Do you have a seconder to 1? Or a different answer? Anybody?
I'd say 1 also.
You say 1. Perfect. Thank you. So I have a seconder to the 1, right? So let's discuss this. So we are looking at the limit as it approaches 2 from the right. So I see 2. Okay, 2 is here. Nice. From the right, oh, that means I have to track the graph from the right. So I see the function going down. Oh, I don't cross over the 2, but I see that, oh, this is approaching what? 1. So that is correct. It's 1. Right? Okay. Please, are you okay with this? Okay. Now, what about the C? For the C, let me talk about it because it's a bit new. Now, we already established in a previous slide that if the one-sided limits are equal, then the general limit will be that number. In this case, you can see that the limit as you approach 2 from the left is 3, and then the limit as you approach 2 from the right is 1. The 2 don't agree, right? They are not the same. So here, this general limit, we say cannot be obtained. It does not exist, right? It does not exist. It does not exist. And in short, in your homework, you see this written as DNE. Does not exist, right? Because the one-sided limits are not equal. Please, are you okay? So we're using DNE from now. So it does not exist. Please, are you okay with that? Any questions? Okay. Now, what about the D? Can anyone please help us with the D? What do you say? D. Yeah, D. Anybody? Any suggestions? What do you think? For D, a proposed answer. What do you say? I said, feel free to speak your mind. Your comments are always appreciated.
2.
2. I have 2. Perfect. Thank you. Anybody else with a different answer or a seconder? A different answer or a seconder? Feel free to use the chat or mute yourself and talk to me, because that's the point. I have to know you guys understand. I don't want to rattle on you and just go. So what do you say? A seconder? Oh,
I agree with 2.
Perfect. Thank you. I have a seconder now. Awesome. Awesome. You guys are cool. So I have a seconder to 2. Now let's talk about this. So for this one, we have, so you're looking at D, right? We have X, limit of G of X as X approaches 5 from the left, right? So we locate 5. So where's 5? 5 is right here. And from the left, so track the curve from the left. So looking at it, it's approaching this point here, right? So that's going to be what? Here. So that's 2. Perfect. So that's correct. Thank you. What about the E? Anybody with the answer to the E?
I'd say 2 as well.
Say 2 as well. Perfect. Okay, so E, let me make its own option here. 2. Yeah, thank you. Anybody else with a do you have a second or a different answer?
I agree.
You agree. Perfect. Thank you so much. Thank you so much. Now let's discuss this, right? So you're looking at the limit of G of X as X approaches 5 from the right. So we first locate 5 and we track it from the right. So from the right, going, oh, okay, then that is here, right? So we are approaching this point here, which is what? 2. So that's also true. Perfect. Please, are you okay? Yeah. So now what about the F? What do you say? What is the answer to F?
Is it 1?
Would that be
So-
1?
Yeah, so good. As I said, always bring your thought. What you think? So I have 1. Perfect. I have 1. Your comments are always welcome. A different answer is seconder. Or did I hear two people speak?
Yeah, I said 1 as well.
Okay, so I have a seconder too. Perfect. Okay, so here in this case, I will say this is incorrect, right? This is incorrect because remember that from this rule, right? From this rule right here, we said if and only if. That means that if this is L, the left-hand limit is L and the right-hand limit is L, then the general one is also L, right? So for this one, you don't even have to look at the graph. Because we already did from the left and from the right and we got the 2 to be 2, the answer is just 2. I suspect that you were reading this point, right? You were reading this point, which is somewhere a little bit above 1, but close to 1. But as I said, when we are looking at the limit last week, we don't look at the exact point. It's possible for the limit as you approach a point and then the value of the point are the same. It's possible. But it's also possible that the function will not even be defined at that point, but we still get the limit to exist. And it's possible that the function at that point and then the limit will be different. So this is a case where it's different, right? So here, the G of 5 is somewhere like, let's say 1.4, something like that. A little bit above 1, you see. A little bit somewhere here. So let's say 1.4, right? You're not interested in the exact value, but the point I want to put across is the limit is not that point, that shaded point here. It's rather what? Tracking this curve and getting this point here, this point 2. So that's 2, right? And that can be either seen from the graph or from the theorem that we just proposed, that the one-sided limit, if they are the same, then the general limit is also the same value. Please, are you okay with this? So that's an important point. Any questions here? Okay. Now, anybody needs time here? So that's how you do it with a graphical technique. Okay. If no one needs time, then this just illustrating like notes on what we did, right? Notes on what we did. So it's just telling us that the A is 3, we got that 1, the B is 1, we got that also. And it says that since the left and the right limits are different, we conclude that what this limit does not exist, right? So that's the D and E. And then this one, we already did this, right? We saw this and talked about this. So this is just notes, right? It's just showing us that this is true, that's true. And at this time, you see the left and the right hand limits are the same. So by the theorem, we say that what this general limit is true, right? Now it says, notice that the G of 5 is not 2. Here, the value of the function at 5 is different from the limit, right? So this is just notes. Okay. Now, we just saw that it's possible for a limit to not exist. It's possible for a limit to not exist, right? So one case that we saw was if the left-hand limit and the right-hand limit are not the same, right? If they are not equal, then we say that the limit as you approach it in general does not exist. But then we begin to be interested. So, okay, when does the limit not exist? When does the limit not exist? Is that the only case where the limit does not exist? Well, it turns out that there are 2 more ways that we are going to see that the limit does not exist, right? So the one way we've seen is if the right hand and the left hand limit they are not equal. If they are not equal, then the general limit will also not exist. But let's look at some other ways in which the limit will fail to exist. Now, to illustrate that, you are just going to investigate this limit, right? So you have the limit as s approaches 0 of sine of pi over x, right? Sine of pi over x. Now for this one, let's look at this. We are approaching 0, right? So this is general. This is not one-sided. This is general. So you have to look at it from the right and then from the left. Okay, so that's why you see the plus or minus here, the plus or minus, right? The plus or minus for here. So you're looking at it from the right and from the left. Now, if you observe the first set, right? So I have like 3 sets of x values here. If you observe the first set, we have plus or minus half, but let's just focus on the half. The half is like 0.5, and then 1/3, which is I think 3333 something. But the emphasis is approaching 0. So 1/3 is also smaller than the 0.5, and then 1/4 is 0.25, which is smaller than 0.5. So it's approaching 0, right? From the left and from the right. This is also smaller, right? This is 0.2. 0.2, and then you can go on and on and on, but for each of these is approaching 0. Now you observe that if you plug these values in the sine of pi over x, you are getting it to be 0. So someone who takes who is trying to use the numerical technique by plugging in these kinds of values, like the half, 1/3, 1/4, 1/5, the person will say, it appears this limit is 0, right? And yeah, I mean, without any other investigation or debate, the person can show it. The person was taking numbers closer and closer to 0, and it was coming out as 0 all the time. So the person said, I think it's 0. Okay. Now let's look at another case. Someone could say, okay, I'm also using 2/3. I'm also going to approach 0, but from different x values. 2/3, okay, and then 2/7, 2/11, 2/15. These numbers are also getting closer and closer to 0 from the left and from the right. But this is giving us -1. So another person who also uses this set of numbers will get the answer to be -1, right? Which is interesting. This person is not wrong. He says that he was using numbers approaching 0 and was getting 0. Another person was using numbers getting close to 0 and was getting -1. A third person is also going to use a different set of numbers which are also approaching 0. Right, from the left and from right. But let's see what that person is also getting. So for the 2/5, 2/9, 2/13, 2/17, this is also getting smaller and smaller. It's getting close to 0 from the left and from the right. However, if you plug this in the sine of pi over x thing, you're getting 1. So that person could also say, well, mine is also approaching 0 from the left and from right, and I'm getting 1. Right? So now, this is another case where a function does not what? The limit does not exist, because you are getting 3 different values, right? Depending on which kinds of numbers you are plugging in. In fact, for this case, as you can see here, you see some dashed lines. You see the dashed lines as you get close to 0. So this is 0, right? And close to 0, you see dashed lines from the left and from the right. What this illustrates is the function itself, it doesn't even take on only 0 and 1 and -1. Someone can also choose a set of s values, which will give it a different number in between -1 and 1, right? Someone could take different values, which is approaching 0, which will give a different number in between -1 and 1. So what is happening is, as you get close to 0, the function is oscillating. The function is oscillating between -1 and 1. So it takes some values in between -1 and 1. So that means that when you're taking the limit as you approach 0, it doesn't approach a single number. It's oscillating between numbers. Finite numbers. So that means that the limit does not exist. So that's the characteristic you see here. You see dashed lines here. So on your homework, you get a question like that. There'll be dashed lines to one side. In that case, the one-sided limit is even oscillating. So the limit does not exist. Please, are you okay with this? Yeah, so that's one way, right? When the function is oscillating between several values as you approach, say, the number that you're interested in taking the limit of. So in this case, we say what? This does not exist. And as I said, I won't give you a function where you'll be doing the numerical. The one in your homework is a graph. You see the graph there. Yeah. Please, any questions here? So that's one case. Anybody needs time? Oh. Okay. So 2 cases now. The limit will not exist if the one-sided limits don't agree, right? The limit will not exist for the general one if the one-sided limits don't agree, right? And then even for either one-sided or the general limit, if the function is oscillating as you take the limit, then it also does not exist. So those are the two cases so far. Now let's look at another case. Let's look at example 6. As I said, I'm just doing this to explain. That's why I'm using the numerical. I won't ask you to do numerical, right? We are just explaining these things, these concepts. Now for example 6, we are asked to find the limit of 1 over s squared as s approaches 0. And you have to find it if it exists. So we have a table of values, right, to check this limit. So we are approaching 0, right? So 0. You are trying numbers bigger than 0, smaller than 0. So they start with 1, -1. So you see -1 is here, 1 is here, and then they will be approaching. So 0.5, 0.2, 0.1, 0.05, 0.01, 0.001. Now looking at these numbers, you see that we have 1, 4, 25, 100, 400, 10,000, 1 million, right? So as you get closer and closer to 0, this thing, the function is becoming very, very huge, right? It's approaching a very, very big number, but it doesn't stick to one number. It doesn't approach a single number. For a limit to exist, it has to approach a single number. The numbers keep getting bigger, but we don't see the end, right? It's just going on and on. So it's kind of like approaching infinity. Infinity is not a destination. It doesn't end, right? So that means for this one too, the limit does not exist, right? So the values of f of s become arbitrarily large, but do not approach a number. So the limit does not exist. So those are the three cases. So either you are trying to find the general limit and then the one-sided limits don't agree. That's one case. And if the function oscillates, right, between several numbers as you get closer, that's also what? Another way where the function will not exist. And then the final case is if it's not approaching a single number, let's say it's becoming very, very big, or it could become very, very small. In that case, approaching negative infinity, right? So that one too, the limit does not exist. Please, are you okay with these points? Any questions? Okay. Now, anybody needs time here? Okay. So now with that out of the way, right, after defining this limit, let's move on to infinite limits and vertical asymptotes. So infinite limit just came out as the last example. You see, this one is an infinite limit because the limit is approaching infinity. So that's a kind of infinite limit. So let's get a formal definition of an infinite limit. So let f be a function defined on both sides of a, except possibly at a itself. Then the limit as s approaches a of f of x is equal to infinity. Means that values of f of x can be made arbitrarily large by taking s sufficiently close to a, but not equal to a, right? Don't forget that for limits, you don't look at the exact value. You're looking at in the neighborhood, right? So as we take the s values closer and closer to a, the function is becoming arbitrarily large. Now, the point is, if I say the limit as s approaches a of f of x is equal to infinity, I'm not implying that this limit exists. The limit does not exist. But infinity gives us more information about how the limit does not exist. You see, so this one is actually, it does not exist. The limit does not exist because we just saw that here in this example, example 6. The limit does not exist. But if I say, as I said, if it's infinity, we rather use what? Infinity rather than say dne. Right? Please, are you okay? Right, so that's why this one says, for instance, for example 6, we have the limit as s approaches 0 of 1 over s squared is equal to infinity. So we rather write infinity than dne. But note that infinity still means the limit does not exist. Right? Yeah. So as you saw, infinity is just a type of what does not exist case. But we rather write infinity to throw more light on which kind of what does not exist it is. Please, are you okay with this? Anybody needs time here? Okay. So with this one, as I said, again, the symbol, this is not a number, right? But the expression is often read as what? The limit of f of s as s approaches a is infinity, or f of s becoming infinite as s approaches a, or f of s increases without bound as s approaches a. Right? So either of these is a good read, how to read it, right? Now let's look at the graphical way. How does it appear when you are graphing, when you use the graphical technique? So for this one, you're looking at a function f of x, which is the in blue, right? And then the A point is here, right? So this question is asking about the limit as s approaches A of f of x. So how do you do it? So using the graphical technique, this one is approaching A in general. So you have to look at it from the left and from the right. So I'll track it from the left. The function is going, it's just increasing, unbounded. And I suspect it's just going up and up. So that means it's approaching infinity. On the other hand, as I approach from the right, I see it's increasing beyond bound. So that's also approaching infinity. So that means that the two are approaching infinity. So the limit as s approaches A of the function is infinity. Please, are you okay with this? That's how you see it graphically. Okay. Anybody needs time here? Okay. Now, on the other hand, we could also have an infinite limit. So there are two kinds of infinite limits, right? The one which is approaching infinity and the other one which is approaching negative infinity. So for the negative infinity one, this is how it appears, right? In the graphical way. So as you approach from the left, you see that the graph is going down, beyond bound, without bound. So that means from the left, we can see that it's approaching what? Negative infinity. From the right too, is going down, without bound. So that one is also what? Negative infinity. Now, because the two agree on negative infinity, we can say the limit as s approaches A in general of f of x is what? It's negative infinity. So that's how it appears in the graphical way. Please, are you okay with this? Any questions? Okay, now with this one, let me point this out. Let me comment here. What if you have a function like so? Let's say here is 0. And then it's like so on this side. And then it's like so on this side. Right, so something like this. What do you have a graph like this? And then I ask you to find the limit as s approaches 0 in general. So let me call this function, this function is y equal to h of x. What do you have a graph like this, right? From the, of h of x, yeah. So from the left, right, you see that it's approaching infinity. And then from the right, so let me write this, from the left of 0, this is approaching infinity. And then from the right of 0, this is approaching 1. From the right, if you track it from the right, you see that it's approaching negative infinity. Now, because the two are not agreeing on a single answer, I would just say the limit as x approaches 0. In general, if I ask to write, to find this, right, you rather write D and E. Right, so do you see the dynamics now? We are writing D and E because the left-hand limit and the right-hand limit don't agree. Well, technically, infinity and negative infinity are D and E. But when they occur, we write infinity or negative infinity. But there's a case whereby even with that one, the one-sided limits don't agree. If they don't agree, we rather write, then we settle on D and E. Please, are you okay with that? Right? So the general limit will only be equal to something if they both agree. In which case, if it's infinity and they both agree on infinity, like you saw in this example. See, for this one, they both agree from the left, from the right and from the left, they are both approaching negative infinity. So we can write that the general one is also negative infinity. From the previous one, from the right and from the left, they are both approaching infinity. So we can write the general one to be infinity. But if they don't, the two sides don't agree, we then settle back on what? D and E. Please, are you okay so far? Any questions? Okay. Okay, so this is just the formal definition for a limit, an infinite limit where we are approaching negative infinity. So let f be a function defined on both sides of A, except possibly at A itself. Then the limit as s approaches A of f of s is negative infinity, means that we can make f of s arbitrarily large negative by taking s sufficiently close to A, but not equal to A. Right? So that's how we write it. And it can be read as the limit of f of s as s approaches A is negative infinity. Or you can say f of s decreases without bound as s approaches A. So this is a classic example of such a function. Right? Yeah. Please, any questions here? Okay. Anybody needs time on this slide? So all of these are just definitions, right? Definitions. And for the graphical technique, you'll be using those in your homework. Okay, now, just as I showed you in the previous slide, we can have general limits approaching either infinity or negative infinity, right? We can have limit as s approaches a in general, not one-sided, to be infinity. We can also have the limit as s approaches a of a function to be what? To negative infinity. Now, the one-sided limits also can hold, right, for an infinite limit. So we can have only from the left to be infinity, or from the right to be infinity, or from the left to be negative infinity, or from the right to be negative infinity, right? But for each of these, remember that the one-sided limit definitions hold, right? So if you're looking at the limit as s approaches a from the left, right, then that means that we are looking at only smaller numbers of a, right? If you're looking at from the right, then we're looking at only bigger numbers, numbers bigger than a, and approaching it closer and closer to the a, right? So that's the one-sided limit as an infinite limit. Okay. Please, anybody needs time here? Okay. So let's look at the one-sided limits, how they look like in a graphical. Well, it's just like the general, but this time around, you're just focusing on one side, right? So the a is showing us the limit as s approaches a from the left of a function to be infinity. How does that look like? So you track a is right here. And then you look at the function, the behavior. Oh, it's going up and up and up. So we know that the limit as s approaches a from the left is infinity. Or we could do also from the right, right? So from the right, this is how the graph looks like. So from the right, you see it's going up and up and up without bound. So we can say the limit as s approaches a from the right of f of s is also infinity, right? We can also have a negative infinity type of infinite limit. So from the left, this is just going down. So it's approaching negative infinity. And this one is from the right, approaching negative infinity. So these graphs are just illustrating how the infinite limits appear for one-sided limits, right? Please, any questions here? Anybody needs time? Okay. Now, we define something we call a vertical asymptote. Now, let a vertical line s equal to a, right? So the vertical line s equal to a is called a vertical asymptote, right, of a curve y equal to f of s, if at least one of the following is true. So you just need one of them to be true. Then you can say s equal to a, which is a vertical line, will be what? Your vertical asymptote. So if one of the infinite limits hold, right, either from the general limit as you approach a is infinity, or the general limit is negative infinity, or one of the one-sided is negative infinity or infinity as you approach that a, then x equal to a is a vertical asymptote. It's a vertical asymptote. Right, so that's a vertical asymptote. That's the definition. Okay. Please, anybody needs time here? So you're going to see how you're going to obtain vertical asymptotes using this definition. Okay. Now let's look at example 7. Now, please pay attention to example 7 because you encounter this almost through the entire course, right? So this one, you have to look at how this goes. Now, you don't always have to obtain a graph of a function to be able to figure out the vertical asymptote. Here, I'm going to show you a technique which you can use to figure out the vertical asymptote. So the question says that does the curve y equal to 2s over s minus 3 have a vertical asymptote? Also, what's the limit as s approaches 3 of 2x over s minus 3? So let's look at this. Now, the function that we have here is y equal to 2x over s minus 3, right? In Math 126, you were taught that if you want to find a vertical asymptote, then make sure that if it's a rational function, right, a function over a function, make sure it's in reduced form. If it's in reduced form, then set the denominator equal to 0, and then the solution to that will give you the vertical asymptote. Now, in calculus, you have to do a little bit more, right? You have to do a little bit more. So the first step is you have to make sure this is in reduced form, right? And then you get candidates for vertical asymptote. So how do you get a candidate? Well, you set the denominator equal to 0, right? So the denominator is s minus 3. So set this equal to 0. And then you're going to get s equal to 3, right? In 126, you just conclude that this is a vertical asymptote. But as I said, in calculus, you have to do more because of this definition. We have to prove that either one-sided is infinity or the general one is negative infinity or something. Or you have to prove one of these. So let's look at this. I think time is almost up. So let me just do for one-sided and then we continue on Wednesday. Right. So let me do from, what do you prefer, from the right or from the left? I'll probably not be able to. What do you say? From the right or from the left? You have to do one-sided.
Right.
Right. Okay, fine. So you have 2x over s minus 3. Well, it's time. It's time. So I'll continue from here. Right. I'll continue from here. So thank you for your time. I'll see you guys on Wednesday. Yeah, that's all for today.
All right. Thank you so much.
You're welcome.
Thank you.
Thank you.
Have a nice day.
Same to
Thank
you.
you.
Guys. See you. Yeah.
Thank you.
You're welcome. See you.
Thank you. Did attendance get taken by chance?
Yeah, attendance gets taken. I think today I'll just check I think I forgot to take it today. So I'll just check what do you call it?
Participants list.
The list. Like automatically when you log on, it's